Good morning to all my dear students. I hope you are well and fine. And now we will discuss magnetic effect of the current. But I want to recall you, previous of the lectures we had completed all these units like electrostatics, electric charge and field, as well as the electric potential and capacitance. And after then we was completing just current electricity, as well as the electric circuit and measurements you know very well, like Kirchhoff's law, meter base, Wheatstone base, potentiometer. It is very easy to understand now for you. And after then, now we will discuss what is the magnetic effect of the current. And I am just also dividing it in the two different parts. In first part, we will discuss how a particular magnetic field will produce. Magnetic field will produce due to the current. First of all, we will discuss. And after then, we will discuss how that particular magnetic effect, magnetic field will provide the effect on a moving charge particle. Okay. So now we will discuss here. First of all, I want to introduce you what is the magnetic effect of current, and we will observe it around 1820. It was experimentally observed by Oersted experiment. We will discuss here. After then, we will discuss what is the Ampere swimming rule. It is a part number 2, as well as third part is here Maxwell's corkscrew rule. How magnetic field will provide the directions. And next point, point 4 is the right hand thumb rule. It was very easy to understand, you know. It was also studied at the class 10th, you know or not? At the class 10th, you know very well what is the right hand thumb rule, left hand thumb rule. And here new terms introduced to you. From here we will introduce a new term, new experimental result, 5th number, which is Biot-Savarts Law. Biot-Savarts Law, it was also invented around 1820, in the same year as Oersted experiment was just experimentally proved that magnetic field will also be produced with the help of current carrying conductor. And next one we will discuss here what is the magnetic field due to the infinitely long straight current carrying conductor. And next part, what is the magnetic field due to a circular current carrying, circular loop. Here it is a long straight wire and here circular loop, ring you can say. Okay. So what should be the magnetic field with the help of that particular condition. And at the last of the study, what will be the effect of the magnetic field, how magnetic field will produced due to a solenoid. It is also, name was also given in class 10th standard. Okay. Now we will discuss what is the magnetic effect of current, and that particular discussion can be experimentally shown by the Oersted experiment. So first of all, I want to tell you what is the magnetic field. The region near a magnet where a magnetic needle experiences a torque and rests in a definite direction is called the magnetic field. Okay, and that particular magnetic field was observed by the Oersted around the current carrying conductor. Now, what is the magnetic effect of the current? You know, here it is given an electric current. What is it? It is a flow of electric charge produces magnetic effect in the space around the conductor, which is called strength of magnetic field, or which is also called the magnetic field. Practically shown by the Oersted experiment, and in that particular experiment, first of all we will show the resistance is connected and a key is connected here. Here a battery is also introduced in that particular circuit, and after then you are just observing a needle. You know very well it is a magnetic needle which North Pole is here, and that particular magnetic needle is just placed blue to that particular wire parallel to it. Okay. In that particular scenario, what will be the experimental result? Just see on the board. When we will insert the key, current will flow through the circuit, and after then we are just observing that it will get deflected. It will deflect in a particular condition. What is the condition for it? According to the left hand swim rule, if that a particular person, suppose that a person is swimming in such a manner In which condition? When current is just entered from his feet and just leave from his head. Then you know very well, during that particular swimming condition, you know left hand will be here and right hand will be here. Okay. So north pole of the magnet must to be deflected towards to the left hand. Okay. Here you are observing left hand is along to that particular direction. Then north pole is get shifted, get deflected towards to the left hand. It is also known as the left hand swim rule. So what is the Oersted experiment? Just observe here. It is given that when current was allowed to flow through a wire placed parallel to the axis of a magnetic needle kept directly below the wire, the needle was found to deflect from its normal position as was observed before 2 minutes. Okay, it was reversed through the wire. In that particular condition, the needle was found to deflect in the opposite direction to the earlier case. How? Just see here, it is given that again same circuit, but in that particular condition you are observing that that particular battery is just opposite to this one direction. Its polarity is just reversed. Okay, and now current will release in that particular direction. How it is possible? You just see here, he is just inserted inside of the circuit and current is just released by the battery, and you will observe here needle get deflected again. What is the difference between these two conditions? You know very well here. Again I will apply the left hand swim rule. A person which is just swimming like that, you know, in that particular scenario, a required condition is current always entered from his feet and just leave through its head. In that particular scenario, you know very well, its left hand will be here and its right hand will be here. And I was just introduced to you, north pole of the magnet get deflected towards to the left hand direction. And you know very well, here that particular needle is directed along to the outward direction. Again I am repeating the statement, when current was reversed through the wire, the needle was found to deflect in the opposite direction to the earlier case. Here what is the difference? It is again deflected, but in the direction opposite to the that previous condition. So it is just a Oersted experiment by which we can say, if a particular current carrying conductor is placed near to the magnetic field, it get deflect. Why? Because magnetic region must to be set up around to it. In 20, he found that a magnetic field is established around a current carrying conductor just like a bar magnet, and the wire is kept always above the magnetic needle parallel to it for observing that particular result. And this experiment shows that moving charge produce magnetic field in the surrounding space. Rules to determine the direction of magnetic field, in which we will discuss Ampere swimming rule, or it is also known as the Snow rule. In that particular condition, just see on the board, statement is given here. Imagine a man who swims in the direction of a current from south to the north facing. A magnetic needle kept under him such that current enters his feet, then the north pole of the needle will deflect towards to his left hand, that is towards to the west. How it will understand here? Just see, and I will clear it with the help of a given figure. Just see on the board, a person which is swimming, and here north and south direction is given. You know very well, and this direction of the swimming is towards to the south to north. Current is flowing along to that particular direction, and you are just observing during that particular swimming condition, north pole of the magnet is get drifted towards to the left hand of the swimmer, and in that particular condition it can also observe with the help of that particular rule, which is also known as Maxwell cork screw rule or the right hand screw rule. But before discussing it, I want to again inform to you how you will understand that particular condition. You know very well, its left hand will be drifted, will be moved along to this one direction, and north pole will shift towards to the left hand, and that particular direction will indicate the west direction. So it is just known as the SNO rule, SNOW. South to north, if current is flowing, south to north current is flowing, then your magnetic needle north pole must be get drifted, shifted toward to the west direction. Okay, along to the screwdriver is drive it along to that particular direction. Then you know very well, a screw will go inside of the any particular substance, and you must to be place the direction of the current along to the movement of the screw, and your finger which must to be rotating along to that particular direction will provide the direction of the magnetic field. In that particular condition, you will get the result. What is the scenario? If the forward motion of an imaginarily right-handed screw is in the direction of the current, so a linear conductor, then the direction of rotation of the screw gives the direction of the magnetic lines of the force around the conductor. Mean to say, you know very well, current will must to be directed. It must to be directed along to the direction of the motion of the screw inside of any substance, and your screwdriver or your finger must to be rotating in a particular direction will provide the direction of the magnetic field. If you will rotate the screw opposite to that particular direction, suppose that you will rotate it along to the clockwise direction, then you know very well screw will release outward. If a screwdriver is moving like that, a screw will release outward. And you know very well, if current is directed in that particular direction, then your magnetic field must be directed along to anti-clockwise direction. Next we will discuss what is the right hand thumb rule or the curve rule. Here you know very well, that particular figure is given, and suppose in that particular condition we will discuss if a current carrying conductor is imagined to be held in that right hand, such as in which hand? Right hand, such that the thumb points in the direction of the current, then the tips of the finger encircling the conductor give the direction of the magnetic line of force. What is it? Please see on the board. Suppose a particular current carrying conductor is given here. It is a current carrying conductor, and you know very well, if current I is directed along to upward direction, and you are just curved it along to your fingers like that. You are holding in your right hand. It is right hand. Okay, right hand. Then, if current is directed along to direction of the thumb, your magnetic field must be directed along to direction of the curved fingers. Okay. Now, after discussing about the rules, right hand rule and all the other rules, we will discuss what is the Biot-Savarts law. What is Biot-Savarts law? First of all, I want to introduce you. The Oersted experiment shows that the current carrying conductor produces a magnetic field. It is clear? And French scientists and the same year at 1820, at the same year, French scientists Biot and Savart, there were two different scientists, in the same year performed series of experiments to study the magnetic field produced by various current carrying conductors, and formed a law to determine the magnitude and direction of the magnetic field produced by that particular conductor. And that particular law is very important to study. It is having very essential role, like Coulomb's law in electrostatic. Biot-Savarts law is playing a very important role in the study of magnetism. Okay, so in that particular condition, you know very well what is the Biot-Savarts law. First of all, it is given in that particular slide. What is the Biot-Savarts law? The strength of magnetic field, which is denoted by the dB, due to a small current element which is known as the DL, carrying a current, suppose that I, at a point P. Here I am choosing a particular point P. Distance small r, that particular point P is at a small r distance. It is distance small r from the element. What is the element? It is element DL. Okay, directly proportional to the current length of the conductor as well as the angle. It is the angle, position angle from the wire to the point P. Okay, so it must be depends upon the all these three values I, dl and sin theta, and inversely proportional to the square of the distance r square, where theta is the angle between the dl and the r. Just see on the board, it is given here. What is the figure? You know that particular conducting wire which is just carrying the current I, and dl element is choosing here. Point P was situated. Now another point I am choosing here, which is known as the P dash, which is r distance from the conducting wire, and all the conditions are given here. So now I want to introduce you. It is suppose named as the AB is a current carrying conductor. I current is flowing through it, and DL is the length element which is just from here to there, and that is the angle theta which must to be placed. DL element is placed from the point small r distance, which is given here. It is a point at which we want to find the magnetic field. So what is the result of Biot-Savarts law? With the help of that particular small element, experimentally it is observed that that particular DL element will provide the magnetic field, and with the help of right hand rule, you know very well, if you will put the thumb along to the direction of the current, then your finger must be curved at that particular point, and you know very well, finger must be go inside of the board at this one point, and it will released at the outside of the board, and we will choose the direction of the magnetic field like an arrow. You know very well, it will have a particular tail as well as the head. You know very well, and in that particular condition, in this one point, head is just moving outward, and here that particular tail is just going inside of it. So it will be the inward magnetic field, and here it will be outward magnetic field. Okay. Now you know very well that particular small magnetic field produced by the small element is known as the DL, and that particular DL will provide the magnetic field. Magnetic field will also be too much small, which is known as the dB. So here dB will be directly proportional to the current carrying conductor. I current flowing through it. dB will be directly proportional to length of the DL element. dB will be directly proportional to the sin theta, as well as dB will be inversely proportional to the distance r from the wire to the point. Therefore, finally we will get the result. dB will be directly proportional to the I dl sin theta by r square. Now we can say it is a just a proportionality sign, and when we will remove that proportionality sign, a particular constant will take place, and which value mu naught upon 4 pi is the proportionality constant for the magnetism, and its value must to be given as the 10 to the power minus 7. You must be learned it. Okay. So here that particular formula will indicate a small magnetic field. What is a small magnetic field? Due to that particular length of the wire in which current is just flowing. Just keep in your mind, current is a scalar quantity, but here I and dl is treating as a vector. For solving the problem of the vector, we will consider a new current element like Gauss theorem. You know very well, area was a scalar quantity, but in Gauss we was just considering a small area vector. Why we are choosing it like that? Because solving the problem related to the flux, which value was given as the dA vector equals to dA into n cap. So here I want to introduce you, individually current is a scalar, individually length is a scalar, but commonly both the products is considered as a vector quantity for whole of the magnetism. Okay, so you must be always remind in your mind. Now you know very well what is the Biot-Savarts law, and after that particular study we will discuss, because magnetic field is a vector quantity, so you must be understand how we will write the Biot-Savarts law in a vector form. Just see on the board, here it is given, and I will explain all these things in front of you how it can be possible. You know very well, dV was given in the previous slide. dV equals to mu naught upon 4 pi ideal sine theta divided by the r square. It is experimental result, like Coulomb's law. It is also experimental output. And here I want to write the dV is a vector. Then it must be written as the ideal vector cross r. How you will write it? Ideal cross r. It is a unit vector. It is slightly confusing for you. How it can be possible? Please see, at the 11th standard, you know very well what was the vector A as well as the vector B, and angle between them was given as the theta. And you know very well, if you want to find the cross product of that particular vector, then it must be given as the vector A cross vector B must to be given as the magnitude of the A, magnitude of the B, angle, sine of the angle between these two vectors, sine theta, as well as the unit vector n cap perpendicular to the both of them. And that particular n cap was holded along to that particular direction. It is known as the n cap. How you was just understand it? With the help of right hand thumb rule. If you are just placing your fingers along A to B, then your thumb must to be curved upward direction. You know very well. You are studying at the 11th standard. Here finally you must to be know it. Vector A cross vector B must to be also directed along to direction perpendicular to these two. Okay. Similarly, here you must to be write the value. What is the value of dV? Please see on the board. dV equals to mu naught upon 4 pi. It is a constant and it is given as the IDL, and divided by the R square. You know very well, it is a one magnitude is given here, and you want to find the another magnitude of the vector. What should be its value? You know, it can also be written as the R. And if you are just multiplying it by R, then must to be dividing it by R also. Okay. And you know very well, in the formula it is given sine theta. Sine theta. And you want to write that particular vector as a dV, then you must to be also write that particular side is as a vector. Then must be any scalar must to be multiplied by the unit vector will provide the direction of the vector. So finally we can get a particular result. dV vector must be given as mu naught upon 4 pi. It is a constant, and in that particular bracket you can easily write now. If you want to write in the vector term, then you know very well IDL becomes a vector, and that particular magnitude R, it can also be written as a vector. So you know very well, but due to the sine theta, here sine theta is given, a cross product will take place and it will be given as the ideal vector as well as the R vector divided by product of these two is the R cube. Okay, so here it must be written in the vector form, and you will get the final formula of the magnetic field, small magnetic field, and finally you will get that particular result here. The value of mu naught is 4 pi into 10 power minus 7, or you can say value of mu naught upon 4 pi is equal to 10 power 7. Its unit is the Tesla meter per ampere or Weber per ampere per meter. Okay, but all these things you will understand after some time very easily. It will be very easy for you. But after then, I want to introduce you what is the conclusion of that particular study. What is the conclusion here? You know, direction dV. dV was magnetic field is same as that of the direction of the dl क्रॉस r. मैग्नेटिक फील्ड आपकी उसी डायरेक्शन पर होगी जिस डायरेक्शन पर आपका dl क्रॉस r की डायरेक्शन, थंब की डायरेक्शन. ये क्रॉस प्रोडक्ट का एक रूल है, एंड यू नो वेरी वेल विच कैन बी डिटरमाइंड बाय द राइट हैंड स्क्रू रूल, जो आपने क्लास 11th में स्टडी किया है. इफ टू क्रॉस प्रोडक्ट्स आर गिवन देन इट्स रिजल्ट must to be two vectors are given, then its result must to be given as the cross product of both of them. And you know very well, I was just introduced to you. What is the direction of the magnetic field? Emerging, बाहर आती हुई, is at the point P dash जो हमने लिया था पीछे, is like a dot, and entering अंदर जाती हुई at the point P, it will be given like a cross. So you know very well, it will be the symbol for the magnetic field, showing the magnetic field at that particular place. And current element is a vector quantity, जिसको मैंने आपको बताया था. What was the current element? IDL is commonly known as the current element, whose magnitude is the vector product of the current and length of the small element. What should be its magnitude? Its magnitude will be I into dl, and the direction of the flow of the current. In which direction it will be directed? It must be directed along the direction of the current. करंट तो स्केलर होती है, लेकिन करंट एलिमेंट एक वेक्टर क्वांटिटी होता है. इसको अपने माइंड में बहुत केयरफुली बैठा लीजिए, जिससे कि आगे आपको कहीं प्रॉब्लम फेस ना करनी पड़े.